Hello everyone and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is best practices for transformer turns ratio testing. My name is Michael Fleischer and I'm the digital marketing specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during our Q&A segment at the end of the webinar. Our presenter today is Daniel Carreño, Applications Engineer. Also, to assist with the question and answer session, we will have two panelists joining us today, Volny Naranjo, Applications Engineer, and Sanket Bolar, Applications Engineer. All right, let's go ahead and get started. Thanks for joining us today, Daniel.
Thank you, Michael, and good morning to everyone joining us this morning for this special sessions of our webinars. As Michael said, today we'll be discussing best practices for transformer turns ratio testing. And once again, this is a special series of our webinars. We have received an increased request, for supports in these difficult, strange times. I hope everyone staying safe and healthy. And again, we decided to extend our webinar series. So since a lot of our daily routines for a lot of people are disrupted, and some of us are finding this time to go back to these projects that otherwise would be on hold. So hopefully today's session will provide you with useful information for your day-to-day activities. I'm gonna divide the presentation of the webinar in two main sections. The first one covering the basic concepts, the when, why we need to perform TTR, right? This is often seen as a very simple topic, right? And sometimes we overlook some facts that will actually help us understand that the test in the field, help us troubleshoot issues, right? When we get unexpected results, that's when this information, knowing the background, knowing what is happening when we perform the measurements, will come handy, will be useful, again, for us to troubleshoot those issues we encounter in the field. On the second section of the webinar, I'll be covering the TTR U3, the latest addition to our Megger family of TTR instruments, and how this new instrument responds to those needs and what features the unit has to help us, again, troubleshoot issues or unexpected measurements when we perform the TTR test in the field. So let's start with the basic concepts, right? And before we dive into what the actual measurement is, what some of the physics behind it, we first need to understand why it's important to measure TTR on a transformer. And you're seeing here a very graphic representation of the power grid, right? Starting obviously from generation, we need to transmit the power, right? You see we have a transformer right after the generator, again, to start transmitting that power to reach both commercial and residential customers, right? And we also see renewable sources of energy also linked to the power grid transformer as well. So we see transformers are, or we'll find this device across the whole range of the power grid. It will be everywhere, right? And in that sense, we'll have many different types of transformers in the power grid, in the power system, right? Obviously, here in the slide you're seeing right now, the pictures are not to scale one to the other, right? I'm showing you a pole-mounted transformer going from left to right, pad-mounted the distribution transformer dry type, then a power transformer, and on the right side, a generator step up, right? A commonly called GSU. So a very wide range of types of applications of transformers. In terms of TTR, transformer turns ratio measurements, we perform the test exactly the same, right? And actually, we can have one instrument, and that one instrument will actually be useful, or we can use it to perform the measurement, the TTR measurement on all these different types of transformers, right? And again, we can say that the way we perform the test is pretty simple, right? And what are we testing, right? Obviously, taking it from the name transformer turns ratio, right? We're looking at the relationship between the physical number of turns between two windings, right? In this case, primary and secondary, right? Is indicated here in this equivalent transformer circuit as NP, as indicating number of turns on my primary winding, and S, which is number of turns on my secondary winding, right? And then again, I'm saying number of turns, right? As owners of the transformer, end user, or the individual performing these measurements, I typically don't know the actual number of turns of any of the windings of the transformer I'm testing, right? That is not something that I will find on the nameplate or on the maintenance manual of the unit. Again, typically, again, as end users or the individual running the test, I don't know that number of any transformer. So what we are actually measuring in the field is the transformer voltage ratio, right? The TVR indicated on that last equation on the right. And then I compare that measurement towards the transformer nameplate ratio, which is the ratio that I calculate from the rated voltage values for each winding of the transformer, and I take those from the nameplate, hence the name transformer nameplate ratio, right? So three different concepts related on the test. TTR, right, the number of turns on my windings, nameplate ratio, which is I calculated from the rated values on my nameplate, and TVR, which is the actual number that I'm measuring with my TTR, right? How do I do that in the field, right? I take my TTR, my instrument, I connect typically to one side of the transformer, apply voltage on one side, and measure the induced resulting voltage on the other side of the transformer. Why do we call it TTR, right? When we perform the test, we do it under one very specific condition, and that's very specific condition is open circuit, no load, right? When we perform the test, there is no load on that side of the transformer. We're measuring the induced resulting voltage, right? So that condition allows us to say that what I'm measuring, which is TVR, right, the one highlighted in green, is equal to my TTR, right? So that is very important. Now, I was showing you a very basic diagram, right? But nowadays, most modern TTRs will have provisions to connect to the three windings of a three-phase transformer, right? As shown in the picture. And again, what am I doing? I'm applying voltage on one side and measuring the resulting induced voltage on the other side of the transformer. On this type of units, three-phase units, right, I can have my windings connected in many different configurations. I'm only showing you a few here, a very few. There are, again, many different possibilities: delta, star, or Y connected windings, T-type, zigzag. I'm showing you also a single phase, right? So when I perform the test, and before we said I have to compare my measurements to my nameplate value, right, to know if my results are within the accepted limits. When I have a three-phase transformer, I need to consider a correction factor, right? It's not a direct ratio as I showed you before, right? Just dividing my primary by the secondary rated voltages. I need a correction factor, and that correction factor will depend on what is the configuration of my windings, the connection I have for the windings I'm testing. The good news is, I mean, back in the day, we used to have a table, right, to look for that specific correction factor I need for the transformer I'm testing. But nowadays, either my TTR, my instrument, or the software in the computer, if I'm using that to control my instrument, will actually do that calculation for me. All I have to do is specify in the software or the unit what is the configuration I'm testing. And again, the software will actually make that correction for me. I also mentioned that we need to compare these values to our nameplate and then determine, right, if my measurements are within the limits. What are those limits? The IEEE dictates plus minus 0.5% of error when compared to my calculated value from the nameplate, right? My transformer nameplate ratio. And I'm showing you as a reference, right? If you want to dig deeper into the standards, IEEE, you can look at two of the publications, the C57.12.90, which is the standard test code, primarily discussing type testing, you know, the validation testing you do for design and what you do at the factory. And when you want to do field test, you need to refer to the IEEE C57.1.152, again, the field test guide for transformer. In terms of requirements, you can also look at NIDES publications, both the acceptance testing standard and the maintenance testing standard, again, indicating how often you need to perform, when, and why you need to perform the test. And even though not commonly used in this side of the world, I'm also showing for reference the IEC standard 60076, which is the power transformers dedicated document, right? So that's on the applicable standards for the test. So now we know the basic, right? What it is and how we do it, what type of instrument I need to perform it. But when do I do it and why do I do it, right? On the when, I mean, if we want to explain it in one sentence, is throughout the life of the transformer. You see here, TTR is so important, right? We are actually testing one of the fundamental functions of the transformer, which is step up or step down a voltage, right? So again, being one of the fundamental principles of operations or fundamental functions of the unit, we want to make sure that we are on the right track when we are designing and manufacturing the unit, right? Hopefully you can see big enough the first picture, the one on the orange square, design and manufacturing. When the active part, right, the core and coil assembly is constructed in the factory, right when the windings are assembled, typically you want to perform TTR just to make sure that there are no either missing or extra turns in your windings. Then you do connections, right? What's commonly called or commonly referred as internal connections. If you need to construct a delta or a zigzag connection or a Y even, you want to make sure those connections are made correctly, right, according to the design. So you do another TTR. Then you do it again in the lab, or when you connect the bushings, or when you connect, if you have a tap changer, right, especially the ones that, let's say 33 steps, all the taps coming out of the windings obviously will go to the tap changer. So when you have those many or that quantity of leads to connect, is easy to make mistakes. So you want to make sure those connections are made correctly. So again, through the manufacturing process, there are many stages where you will perform TTR. So very important test. Then we go to acceptance and commissioning right at the lab, and then when the transformer reaches the final destination where it will be commissioned, TTR will be essential to perform. Then when we go to maintenance, again, TTR is part of the essential measurements you need to perform. And on the last one, obviously, on that picture at that point, sure, you cannot do TTR, but if you have a fault, a true fault, or any kind of suspected major damage, you want to perform, you perform TTR, and I would say along with insulation assessment. Those are the two main tests that you want to run to make sure you still have a functional transformer, right? On the why, well, you already said what are the stages where you want to perform the measurement, but what type of problems can you find when you perform the TTR, right? On the manufacturing part, already mentioned improper number of turns, either less or more turns that the design dictates, incorrect polarity, right? We can assemble the windings or connect them in an incorrect way, and also, again, when constructed, the necessary vector configuration of a Y or a delta, mistakes can be made on that part during manufacturing. Insulation failure, right? When we have damage in the turn-to-turn insulation that will result in shorted windings, and it's something that will be reflected in the TTR results. And we also mentioned tap changers, right? Either a defective unit, a defective tap changer, incorrect assembly or connection, or again, just wear from the unit being in the field, or because of a fault, right? Any malfunction related to the tap changer is easily identifiable with a TTR measurement, right? So that's on the why and what type of issues we can find when performing TTR. Again, a very simple test, but it can give us very important information on our transformer. So now we know the basic part, when we need to perform it and why. When we perform it in the field, and we, as I mentioned in the beginning, we get unexpected results, numbers that are outside the limits, right? The plus minus 0.5% that the IEEE indicates. As I also mentioned in the introduction, then what do we do, right? We can retest it, sure, but if we are repeatedly getting these numbers that are outside the limits, then we need to look at, is it my transformer that is failing? Is it my instrument that is not working correctly? Or am I measuring incorrectly? I'm doing something, is it something in the process, the way I'm testing? Am I doing something incorrect, right? So four main external factors that will affect the results, right? Other obviously than I have an issue with my transformer or my instrument. What are the factors that will actually affect my results in the field? Test voltage, step up versus step down technique to perform the test. I will go a little bit deeper on all of this. Per phase versus three-phase energization, right? If I'm either energizing one phase at a time when I'm testing a three-phase transformer, or if I'm energizing the three phases simultaneously. And finally, the transformer configuration, right? We briefly talked about that, the configuration of the windings, or how many sets of windings I have. That's also an important factor to consider. So let's look at the first one, test voltage, right? When I have my instrument, again, most modern units will automatically select my test voltage, but those will also have an option for the user to actually configure the test voltage, and you obviously have a defined range, right, depending on the instrument you are using. But what's the effect of testing at different levels of voltage for that voltage that I'm applying on the one side of the transformer? So let's look at one example here. This is a DYN1, right, a delta primary Y with the neutral accessible on the secondary, 138 kV primary to 4.365 kV on the secondary. And this is performing the traditional standard way of doing what we call step down, right? We apply the test voltage on the high side and measure on the low side of the transformer. On this example, we did the test, and these are results from phase A of that transformer. So first test, 8 volts. We see the error is 0.73%. We're right there outside the limits, right? If my unit can only do 8, my TTR can only do 8 volts, then on this case, I would deem the transformer with an issue and then just flag it for a deeper investigation on why my TTR is outside the limits. But what happens when we test at higher voltage? You see, going from 8 to 40, the error goes down to 0.27%. And as I increase the voltage all the way to 125 volts, my percentage error goes down. Really important to say, and again, first glance, you can say, well, you are not making the transformer better, right? This is showing a voltage dependency for the test on this transformer, right? And all transformers have a degree of voltage dependency, right? We are obviously not testing at rated voltage, right, which is 138 kV, with a much lower value, but the principle of operation doesn't change. It's just that, again, we are looking at a voltage dependency when we perform the test. Let's look at another example, right? In this case is also energizing the traditional way, right? Energizing the high voltage side of the transformer. Single phase excitation, that means we did the test one phase at a time. And on this graph, I'm actually showing the 3 phases. And you see the same behavior, right? Going, in this case, we tested at 8 volts, 24 volts for the orange bar, and 48 volts for the green one. So you see how the error, again, this graph is showing percentage error, is going down as I increase the voltage, and we didn't even reach the 125 we did before. So higher voltage, better accuracy of my results. I'll go deeper in a couple slides ahead on why we see this kind of behavior. Right? Then we look at step up versus step down. As I already mentioned, the typical traditional way to perform TTR is step down. Many reasons. The main one I would argue is safety, right? As a instrument or test instrument manufacturer, you obviously spec your instrument a given TTR for a certain range of ratios, but then again, that range is typically wide. So you don't know if a user will be testing transformers with ratios of, let's say, 0.5 or with ratios in a few dozen or hundreds, right? So it's easy to say, well, if I spec my instrument to have this much voltage for the output and we do step down, you know by default that you will always be measuring a lower voltage than your output, right? You're always stepping down the voltage. So that again will allow you to spec the unit to determine its insulation levels. And again, it will make the instrument safe to use in the field, right? When you have a unit that can do step up, right? Obviously the opposite, applying voltage on the low voltage side of the transformer and stepping it up to measure the induced voltage on the high voltage side. Well, that instrument is really important that it accounts for that induced that higher voltage that it's gonna induce, right? So it's really important to highlight that if you want to do a step up, you need to have an instrument that is capable of doing it. Or you want to know and to limit that voltage on the high side, to save levels both for the instrument and, more importantly, to the individuals involved in the test. But why step up? And obviously stepping up the voltage will improve the accuracy of the test, but why is the test voltage and stepping it up the voltages, it increases, or you will yield better accuracy, right? If we go back to the initial part of the presentation, we said we're applying a voltage and inducing a voltage on the other side of the transformer, right? So when we apply the voltage, right, the current that my instrument will need to supply is what is excitation current, right? The current needed to actually establish an electromagnetic flux in the core and then induce the voltage on the secondary side of on the other side of my transformer, right? Typically, my low voltage windings will be closer to the core, right? In a core type design transformer, which is probably the most common one. So again, the low voltage winding being closer to the core, and remember, we are testing at much lower voltage typically than rated voltage for transformers. So when I apply voltage on my low voltage winding, or a winding that is closer to the core, the mutual flux, the coupling coefficient, right, that will be better than if I apply voltage on the high voltage side, which is further from the core, as I have more space for insulation and cooling, right? So the flux that I establish in the core, the instrument establishing in the core because of that applied voltage, is a function of volt per turns. So that also explains why using higher voltages will increase the flux and yield better accuracy when performing the test. So let's look at some comparison between step up and step down techniques on the same unit, right? In this case, a YND, right? A star connected winding on the primary, a delta on the secondary. And look, this is really interesting, right? In the single phase excitation step down, the traditional way, we were using 80 volts, right? When we switch to step up, we're actually using 10 times less voltage for the measurement, and even then we are getting way better accuracy for the test, right? I mean, if we look at phase C on this example, with step down, we were very close to the limit, 0.5%, and we were using step up, again, 10 times less voltage for the test. Very, very small error. And again, we are not making the transformer better if we are getting just better accuracy for our measurement. Let's look at another example. In this case, this current combining for the next important factor, which is three-phase excitation. You see, when we did step down, well, I shouldn't say most, but many of my C-phase measurements, this is a 33 tap graph, right? With a transformer with a tap changer. Again, if we look at phase C, some of the taps are outside the 0.5% limit. And if we look towards the end on the 14, 15L, 16L, taps from phase A and phase B are also outside the limit. Is this transformer showing some damage? Let's look at the same test using step up excitation, right? Energizing the low voltage side of the transformer. We see the error is very small compared to the previous result. So now let's look at that effect as well, right? Using the same voltage, but just going from single phase excitation to three-phase excitation, right? Doing either one phase at a time versus the three phases simultaneously, right? You see how the error in this case goes, moves closer to the zero area in the graph, right? And really important to note all this, I mean, except tab number 1, all the errors are negative. So that's why the curves move towards the on the upper direction. Next example, also comparing single phase versus three phase excitation. Once again, showing for the first and second bars negative errors. So when I do three phase excitation, my error will come closer to zero. In this case, I'm also showing the kind of the combined effect of three phase with different voltages. And finally, the transformer configuration, right? When we have a delta secondary, when we have a winding, a transformer with three sets of windings, an auto transformer with a tertiary winding, right? If you remember, again, going back to the initial part of the presentation, we said that when we perform the test, it's really important that on the measurement side, my windings are open circuit, right? If I'm testing with an instrument that is doing single phase excitation and I have a delta secondary, right? That side of that I'm measuring the induced voltage is a delta. Then that condition of the winding being open circuit doesn't hold true, right? My other two untested phases, the other two untested windings of the delta are actually loading the winding under test. So that will affect accuracy when performing the test. And that is why when I energize more than one phase or the three phases at a time, I will get better accuracy for my measurements. So now that we looked at the basic concepts, when and why we perform the test, and what are the factors that will affect my results, right? What are those external factors that will come into play when performing the measurement? How does the new TTR U3 respond to those needs, right? Let's look first at the most important features of the TTR U3. The first one, and hence the name, it's a true three-phase output, right? So the unit will be able to energize the three phases of my transformer simultaneously. Again, hence the name. Higher accuracy, right? Plus or minus 0.5%. And really important that this accuracy, this very high accuracy, is guaranteed in a very wide range of temperatures, right? From minus 20 degrees Celsius all the way to 50 degrees Celsius, right? That means repeatable results no matter the conditions. Another highlight is that the unit, right, being able to energize the three phases at a time, it will generate its own test output. So you can actually power up the unit with an inverter, with a generator. It won't affect the results in those cases. And finally, the third major feature is three-phase step-up, right? It's a patent-pending algorithm that will actually perform a step-up test, assuring that you will never, or the instrument will never have to deal with voltages more than 250 volts, right? So the unit will check the ratio of the transformer and then adjust the output. So again, you never will deal with more than 250 volts. It's really important to highlight this, right? Again, when you want to perform a three-phase step-up measurement, make sure that you have a unit that is capable of performing the test that way. Let's look in a little bit more detail about these features. And the first one is the three-phase setup and output, right? When we look at the traditional TTR, right, a lot of times we call these units three-phase TTR, right? And in the sense that, as I'm showing you right here, I have the capability of connecting to all the windings of the three phases of my three-phase transformer. And this is important mainly for safety, but it will save a lot of trips up and down the ladder if I'm testing a large transformer. It will save me some time, but what happens when I run the test? And I thought it was useful to show you, right? In this case, it's a delta-delta transformer. And again, I have a three-phase unit, which has a single phase switching source internally. So when I press the play button or I start the test, what the unit will do is first energize, in this case, phase A, get the measurement, switch then to phase B, get the results, switch then to phase C, and get the final number for this initial test. Comparing that to the TTR U3 or a true three-phase output, again, same thing. I have provisions to connect to all three phases. When I press the play button, when I start the test, all phases will be energized simultaneously, and I'll get my measurements quicker. How quicker? In this case, comparing a single test, you can go from about 30 seconds in average, right? Comparing many different single source units to 10 seconds. And I mean, one can argue, right? Well, sure, it's a 66% faster time, but well, when I see the big picture, right? Everything that entails running a TTR test, right? Getting the transformer isolated, getting, I don't know if I'm testing just like in the picture, a large unit, getting provisions to go up and make connections. 20 seconds, maybe you don't see that as a big time saver, but what happens when you are testing a transformer with a tap changer, right? If we look at just a transformer with only a low tap changer, you will go from about 16, 17 minutes to less than 6. Or when we compare a transformer, right, for commissioning, if I'm testing a unit with both a de-energized tap changer and a low tap changer, I go from about 80 minutes to about half an hour, so approximately an hour faster. So that's a big time saver. And remember, it's not only that you're getting the results faster, but you're also getting better accuracy, right? Because you're energizing simultaneously the three phases of the unit, and you can also perform the measurement using the step-up technique. Next is step up versus step down. This is great since you don't have to perform any change in connections, right? As you can see, the leads in the test are identified by high voltage and low voltage. If you want to perform step up, all you have to do is click that mode or select that mode in the unit, and the unit will switch the voltage source to the low side. As you can see, I'm gonna go back, right? So my red glow is indicating which side of the transformer is being energized. This is the traditional way, step down. When I go to step up, I'm energizing the low voltage side of the unit. And remember, every transformer will show some voltage dependency, some obviously with a higher degree than others. And this has to do with the core material, the windings, type, and construction, right? So a really, really important feature. Now I briefly mentioned, right, the colors of the leads. That will make the leads easy to identify from the ground, especially when I'm testing very large units. My high voltage winding lead, as you can see now, will be red. The whole cable is red. My low voltage winding is black. Both the cable and the connector of each lead is black. And we also added color-coded clamps for the phases, so it's even easier to connect reduce the chance to make mistakes in the field. And even better news is that these leads are backwards compatible with our other TTR instruments, right? The old TTR three-phase series, the combined unit for winding resistance, and TTR, the MWA, the MTO units, right, to perform winding resistance. So the leads are backwards compatible. That for those older generation units, you need what we call Megger the octopus, right, to make these units will have a single connector. So backwards compatible with older generation units. So that's on the hardware side. Now the software was another section or another part that we at Megger put a lot of thought to make TTR easier, more accurate, give you more actual useful features to help you perform the test in the field. So the first one, what I'm going to show you is simulation mode, right? Which is, again, everything that I'm going to show you in the presentation was captured using simulation mode, which is great for training. When you have the software installed in your computer, you just launch it. I mean, it's the exact same software to control the unit. When you do so, just make sure you don't have your TTR connected to the computer. After about 10 seconds, the look for an instrument will time out and the software will suggest to enable simulation mode. So you accept that suggestion and you get to the main screen, right? Which is this showing the quick test, a new test plan or magnetic balance, and as well as the settings and the about, which will tell you the version of the software. So let's look at first at the quick test, right? A very efficient way to run a measurement, right? Especially in those situations of urgency. When I go to that screen, first selection I have to do is just the vector that I'm testing. In this example, a DYN1. So I select my vector, I will get to this screen and I'm ready to test. I don't need to specify anything else. If you notice, the test mode is by default selected as automatic, so the unit will determine the best way to perform the measurement, either step up or step down, single phase or three phase. And my test voltage is maximum 250 volts. That's also really important. So I press the big green button, which is the test button. Now I'll get my results screen. Remember, after about 10 seconds if I'm doing the three-phase excitation. Really important here that the software is already highlighting a higher than normal, right? 0.78% error when compared to nameplate. The next feature is test plans. You saw that other big button in the home screen. And when I go to that section of the software, it will look like this. On this case, I'll have the opportunity to fill out the nameplate of my transformer. And that will take me some minutes, but it will give me a lot of advantage when performing the measurements. So let's see. So I first need to indicate also the vector if I have a tap changer on what side of the transformer and what type of tap changer is connected to that winding, the number of taps for each of the tap changers, and the voltages, right? Nominal and the higher and lower or the first and last tap for that specific winding. Then I go to the tabs to again select those configurations. I also have the chance to indicate extra asset information, not strictly necessary for running the measurements, but really nice to have this in the report that will be generated automatically at the end of my test. So I can indicate the class of the transformer, the type of tank, the core design. If I have a job number to identify this measurement, I can indicate that as well, manufacturer, the type of coolant, and so on and so forth. So again, I can even include a nameplate picture. So just to make my report more complete and more presentable when I finish my test. Next tab is test conditions, right? The type of weather I'm testing out, the ambient temperature. Even though TTR results are not corrected by temperature, it's important to put those factors or those that kind of information in my report. And why am I performing the test? Is it acceptance? Is it maintenance? Or is it because of a fault, for example? Then when I'm ready to run my test, if you notice my test setup, my last screen for a test plan is exactly the same or identical to the quick test. So less training required. And as you can see from the screenshots, the software is really, really user-friendly. So a lot of visual design, less text. So I think this will translate to less training required when you give the instrument to a person for the first time. It will take them just a few minutes to get familiar with the software. When I run my test, then I go to the results screen, and you see I have a button on the left that says view. So I have three different ways to look at results. The first one is the one that I'm showing right now, right? It will show you results for a single tab, right? If you remember on the previous screenshots, we configured a transformer with both a DETC, a de-energized type changer on the primary, and a low type changer on the secondary. So the upper section is telling you what combination of tabs, what positions the screen is showing. So in this case is primary tab number 1, secondary tab number 16L, right? And it's also showing you the nameplate voltages for those tabs and obviously the results. If I don't like the numbers, if I'm looking at something that doesn't look right, I can just directly retest that tab with this button, right? You obviously need to make sure that the tab changers are in that position that the upper indicator is telling me, and I can quickly retest that position of my tab changer. I can delete these results, edit my setup. Maybe I notice here when I come to results that I incorrectly put something in my test plan, I can correct that, export these results, and change the view, right? So let's look at the second option, which is an error graph. Really useful when I'm testing a transformer with a tab changer. So seeing the results in a graphical way, and it will show both the limits based on the settings, right? If I go to the settings of the software, I can specify different error allowances for a measurement. In this case, the x-axis is just telling me that my secondary tabs are shown. And I can change the graph to show a particular phase or all three phases like I'm showing right now. And the last view is the summary, right? It will give me a summary of all the measurements in that transformer. And from here, I can just export the results. It will show the test date and time, how many tabs were tested. If any of those fail, in this case, I don't have a failed tab. That's why it's showing green. But in case I have a failed measurement, it will indicate so in this section of the screen. It will also show me the test voltage. Right now is showing 0, as you can see right next to that voltage arrow. This was done using simulation mode. That's why it's showing 0. And I can delete the whole test if I need to do so, right? Another important feature, if I'm testing transformers that are similar to each other, I don't have to go through the whole process of the test plan, even though it only takes a few minutes, but I can copy the setup so I can even quicker get ready to test a sister unit or just a transformer with a similar configuration, right? Another feature of the software now is what we call Onetouch OLTC or auto OLTC testing, right? As you can see, I have that in a glowing red square. We include a cable for the tab changer shown on the left, which you will connect on that wide port of the TTR, right on the connection side. Connect that to the control cabinet of your tab changer. And then on the top panel of the unit, we have the switch, right, labeled as OLTC. As you see, you have a position to go up and a position to go down in your tab changer. So you have direct control of the tab changer from the unit. And better yet, those changes, you can do them obviously manually with the switch, right, that I'm showing right now. But the Onetouch OLTC, you have two ways to configure it. The first one is just by you manually indicating the software what is the pulse time and the wait time for your tab change. The pulse time will refer to how long the TTR will actually maintain the pulse to change the position of the tab change, either up or down. And the wait time is how long the tab changer will take to go from one position to the other. So that is the manual way of configuring the timing of the tab. But if you see, I have another big button on the left that says tab timing. So you can use the switch, right, to make the instrument learn the timing of your tab changer, the tab changer you're testing. And once you have that setting configured, the timing of the tab, then you go to your test plan, right, and select OLTC as auto. So that means Onetouch testing, right? You tell the software, I want to start measuring, let's say I'm testing a winding pair with a low tab changer on the secondary, and even though I have 33 tabs, I want to start just from the nominal going down to 16 now. So you indicate that here, start tab. Then you indicate an end tab. If you want to finish, maybe you want to only test the first 5. You indicate the end tab here, click start, and you will get this screen. The first one, which is testing the first tab you indicated. In this example is 1 on the primary, 16R for the low tab changer. Then the unit automatically, without you doing anything else, will do the tab change, right? It will go back to testing, showing you now, in this case, 1 and 15R. Once it has more than 2 tabs on the testing screen, it will show a graph of the results, and it will continue the cycle, right, until it reaches either the last tab that you indicated in the settings, or if the error limit exceeds your settings. And that feature can be turned on and off. Even if you have it off, it means that even if a tab exceeds the error, it will continue testing until it reaches the last tab. At the end, you can look, as I showed before, look at the results in the graph, right? In this case, just to make it more visible, the graph will actually show my error limits, so you can quickly have a glance of what tabs are failing, right? It will also show in the top section what is the maximum error measured during the test. So those are the main features of the software, right, of the new TTR U3. Again, we think the features are actually very useful for field testing. One second here, selected the wrong slide. Once again, we think these features are actually pretty useful, right? And now that you have a little bit deeper information on what comes into picture, right? What happens or how the test voltage affects my results if I'm using step up or step down technique to measure my TTR, if I'm using single phase or 3-phase excitation, and what type of transformer I'm testing, right? These features and the TTR U3, I mean, apart from the advantages that I explained, can also be really useful for special applications like phase shifting transformer and zigzag transformers. The unit will make testing those type of units easier and faster, right? And we also included magnetic balance as a feature, right? So in general, the feature will help you not only improve testing time, but also perform the measurements in a more accurate way, and even we think also safer, right? With the provisions for stepping up and the type of leads and all the software features, I think is an all-around excellent TTR option. If you need more information on the unit, you can go to our dedicated websites for the TTR U3, either megger.com/TTRU3 or TTRU3.com. If you still have questions, for sure you can contact us to schedule a one-to-one webinar. We'll be very happy to set that up if you want us to do again a dedicated webinar for you and your peers, or if you want to see how the unit performs in the field, you want to use it yourself, for sure you can contact us to request a demo unit for you to evaluate with your peers. So I leave you with both my contact information as well as the sales department for the NAFTA market. And with that, I'll turn it over back to Michael in case we have any questions from our audience.
All right, excellent. So at this point, the presentation portion of the webinar is officially concluded. We'll take a few minutes to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate if you would take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or a quote on any Megger products. A copy of the presentation, along with a link of the video recording to the webinar, will be emailed to everyone in about a week. You can also view video recordings of previous webinars on our website at us.megger.com/webinars and register for next week's webinar, Current Transformer Testing and Field Challenges. The presenter will be Abel Gonzalez. All right, let's take a few of your questions. We have a few minutes. So the first one is going to be directed at Sanket. Do all transformers go through the TTR at the factory? Are test results available to the transformer purchaser? Well, it looks like we have Sanket.
I can answer
Sorry,
that. Michael,
Can you hear me now?
Yeah, I can hear you now.
Yes, Sanket. Okay,
Yeah.
go ahead, Sanket.
Okay, sorry, I was muted. Okay, to answer the question, the TTR test is considered a routine test going by the IEEE standard, which is IEEE C57.12.00, and that's the standard for the general requirements for liquid immersed distribution power and regulating transformers. So that particular standard lists the TTR test as a routine test, which means that the manufacturer needs to do this on every transformer, and the ratio values need to be as per the design specifications. So yes, if it's a routine test, the customer should be able to get these results from the manufacturer. At the factory, I should also add that at the factory, it's done as acceptance testing. Besides that, also in-process testing is carried out by manufacturers of bigger power transformers, where at different stages during the manufacturing, this test is carried out, and this test holds a lot of value because not only after the transformer is manufactured, but also during the manufacturing process.
All right. Also for you, Sanket, up to what percentage of error can we say that the readings are okay? What are the steps to be taken if error percentages cross that limit?
So the same standard that I mentioned in the previous question, C57.12.00, states the tolerance for the ratio limits as 0.5%, 0.5%, and that 0.5% is with respect to the nameplate values, and that's the default limit that's set in the software as well. So if the results are outside those limits, the first thing that you want to make sure is that it's not an operator error. Check your tap voltage. Check your tap position. If you're testing on a tap on a transformer with a tap changer, make sure that you're testing on the right tap position. Because if you're testing on a different tap position, then the nameplate voltage would be different than the measured values that you're getting, and that would result in a higher error. The other thing that you want to make sure of is that the vector group is selected right. But things like selecting a wrong vector group would result in an obvious error, and the ratio errors that you would get would be much higher than 0.5%. But these are the two main factors which come into play, which you would want to look into to avoid operator error. Besides that, if the value is actually high, even if you did the testing in the right manner and still the value is high, then there's something wrong with the transformer, and it needs to be investigated. And it may be that the transformer is designed in that manner, but again, like I said, the standard says that 0.5% is the limit for transformers.
All right. It looks like that's all the time we have for, unfortunately. We apologize if we didn't get your question today, which there are a lot. We'll try and follow up with you offline in the next couple of weeks because we do want to answer those questions because they're really good. We just don't have the time for them today. But thank you all for attending. If you could, please remember to follow up with the survey. The survey will also include a field for you to request a demo or a quote if you're interested. But thank you all again for attending, and I hope you have a great week.